This video is the second of my series on the information universe theory. In this video, we will cover the basics of quantum mechanics. Don't worry, I plan on keeping the math to a minimum. This video is primarily laying the groundwork for what is to come. The double-slit experiment is based on the wave-particle duality of subatomic particles. As simple a concept as it is, it produces some of the most astounding experimental results of quantum mechanics. This experiment stands at the heart of quantum weirdness because it is one of the strangest results in science. The original double-slit experiment used photons of light, but later versions used electrons, but the results were the same. The double-slit experiment is actually responsible for starting quantum mechanics. Shooting classical particles, that is, small balls of matter, at a screen with a single slit in it produces a simple spray of particles on the second screen behind it. A good example of this would be bullets shot from a gun at a screen with steel that they cannot penetrate. With one slit in it, you would get just this type of pattern. When a wave passes through a single slit, it produces a pattern that has a bright spot in the center and dims as one moves away from the center. A wave of water passing through a single slit is a good example of this effect in action. When you add a second slit, the classical particles would tend to form two sprays of particles on the second screen. This is the pattern made by bullets shot from a gun at a sheet of steel that they cannot penetrate with two slits in it. When waves pass through a double slit, it produces the bright and dark stripe pattern seen here. This pattern results from the interference of the two waves produced by the slits. This effect can be seen in a wave of water that passes through a double slit. Here is a side-by-side comparison of the two patterns. The top is the pattern produced by classical particles, and the bottom is the interference pattern produced by a wave. Shooting quantum particles, that is subatomic particles, at a screen with a single slit in it produces a simple spray of particles on the second screen behind it. So far, so good. This result is actually consistent with both waves and particles. Now this is where things start getting strange. When shooting quantum particles at a screen with two slits, one would expect to get two sprays of particles on the screen, like what you get with classical particles, such as bullets. However, when one actually shoots quantum particles at a screen with two slits in it, like a wave, quantum particles form a series of several light and dark strips, as shown here. This shows the wave nature of quantum particles. One possibility that was considered is that quantum particles are somehow interacting to form a series of light and dark strips. The solution was to shoot the particles one at a time so that they cannot interact. Here is an illustration of the results of this experiment. Note that the electrons still form an interference pattern, even when shot one at a time. This shows that the wave nature of subatomic particles is inherent in each particle. These results actually seem to require each electron to go through both slits at the same time. However, this is not the end of quantum strangeness, because it gets even stranger. The notion that one particle could actually go through both slits at the same time is so anti-intuitive that physicists had to look to see which slit each particle actually went through. To look, experimenters put detectors by the slits so as to look to see which slit each particle actually goes through. What they saw was a real mind-blower. The result was that the subatomic particles formed a single line behind each slit, just like classical particles would, suggesting that subatomic particles somehow knew when they were being watched and behaved differently because of it. Even this is not the end of the strangeness, because things are about to get even stranger. Suspecting that the detectors were causing the different results. Experimenters turned off the recorder while leaving the detectors on. This process also included the recorder being on but not actually recording anything. To everyone's surprise, they got the interference pattern. Experimenters even had the recorder on, but the tape was removed while leaving the detectors on. They got the interference pattern. The subatomic particles only produce the double lines when the information about them was actually being recorded. This was really strange indeed, because it could only be concluded that it was the act of measurement that affected the experiment and not the measuring devices themselves. All of this is part of particle-wave duality. It is the principle that particles exist as both particles and waves. The waves are not waves moving through a medium like sound or water waves, but they are waves the probability has to where you will find a particle. The result is that every particle of matter has both a wave and a particle nature. The first formula here is the formula for the de Broglie wavelength. The second formula is the relativistic formula for momentum. And the third formula is the de Broglie wavelength in relativistic terms. The relationship between the de Broglie wavelength and a particle's momentum is an important part of quantum mechanics, and it is a key to understanding how light works. It is an important key to understanding quantum mechanics because it is one of the foundational principles of quantum theory. The uncertainty principle shows that there is a fundamental limit to the accuracy with which the values of certain pairs of physical quantities of a particle can be known. A prime example is position and momentum, which is the primary representation of this principle. The wave function of a particle represents the behavior of that particle. It also provides the probability where you will find that particle. For a free particle, the wave function is in the form of a plane wave. This is the time-independent Schrödinger equation. It is the equation that shows the relationship of the wave function to space and energy. This is the time-independent Schrödinger equation, which relates the wave function to both space and time. Combined, these formulas are the foundations of quantum mechanics. Do not worry if you do not understand Schrödinger's equation. That level of understanding is not necessary for you to understand what follows. Quantum field theory says that there are certain basic fields that occupy every point in space-time, and they are what make up the world. Furthermore, particles are excitations in these fields, making up what is called the standard model. These fields interact with each other, resulting in the phenomena we observe, including the matter that makes up our own bodies. This leads to an interesting question, and that is, what exactly is a field? According to physics, a field is a physical quantity represented by a number or tensor that has a value in each point of space and time. In short, fields are mathematical objects, not some kind of physical substance. For example, the temperature field of a room consists of the temperature values at every point in the room. What all this seems to indicate is that the particles that make up everything we know represent particular values in purely mathematical objects. This raises a very interesting question about the nature of reality. Since numbers and tensors are primarily types of information, it suggests that our reality is fundamentally information. Which-way path experiments are variations of the double-slit experiment that test different aspects of what was originally discovered by the double-slit experiment. These experiments explore different ways of detecting which-way path information, quantum behavior of different particles, and different types of which-way paths. They all show the same pattern. When which-way path information is knowable, there is no interference. When it is unknowable, there is interference. The goal of these experiments is often to probe the limits of this quantum behavior. The delayed quantum erasure is a variation of the double-slit experiment that shows that the change from an interference pattern to two spots is not a result of interference from detectors, but from whether or not which-way path information is known or potentially known about the particle. Furthermore, whether or not which-way path information will be detected is determined 8 nanoseconds after the signal photon has already been detected. The basic setup sends a laser light through a double slit, one photon at a time, with a BBO crystal to split the incident photon into two entangled photons. One, which is called the signal photon, goes through detector 0, and the other, called the idler photon, is detected by detector 1, detector 2, or detector 3, 8 nanoseconds later. Detector 4 was not used in the original experiment, but is part of the basic setup. This is an illustration of the delayed quantum erasure experiment. S is the light source. A and B are the two slits, shown in green, with a BBO crystal, shown in yellow, behind it. DO is the detector of the signal photon. BSA, BSB, and BSC are beam splitters. MA and MB are mirrors, and DO1, DO2, DO3, and DO4 are detectors for the idler photon. When the idler photon reaches BS or BSB, half gets reflected to DO3 and DO4 respectively. The other half is transmitted and goes to BSC, where it can be reflected or transmitted to DO1 or DO2. If a photon is detected at detector 3, it could only have come from slit A. As such, it provides which-way path information. And in the experiment, it did not produce an interference pattern, but produced a spot behind the slit, as seen in the classic double-slit experiment. If a photon is detected at detector 4, it could only have come from slit B. As such, it provides which-way path information, and it would not produce an interference pattern, but would produce a spot behind the slit. Here is the actual data from the quantum erasure experiment. You will note that detectors 1 and 2 both produce interference pattern, while detector 3 did not. This thoroughly illustrates what I have been describing. These results show that the change in the pattern of particles does not result from a detector disturbing the particle, since there is no detector at the slit. This fact is enhanced by the fact that the signal photon is detected before the idler. The only variable in the results is the fact that detector 3 and 4 contain which-way path information, and detector 1 and 2 contain no which-way path information. That means that the existence of information about the slit the particle came through, or lack thereof, is what determines whether it behaves like a particle or a wave. The Mach-Zehnder interferometer is designed to measure phase shifts in a beam split from one source. It also has been used in which-way path experiments, using a single excited atom to detect which-way path information. In this experiment, because path A and path B have the same length, quantum interference produces a probability of 1 of the atom being detected at detector X and a probability of 0 of it being detected at detector Y. This differs from the classical prediction of a probability of 1/2 for the atom being detected at either X or Y. In the Mach-Zehnder interferometer, S is the source of the atoms. BS1 is a beam splitter that separates paths A and B. MA and MB are mirrors along paths A and B. And BS2 is a beam splitter that combines paths A and B. DX and DY are detectors. Now, if a single excited atom is passed through the Mach-Zehnder interferometer with non-destructive detectors DA and DB, causing the excited atom to drop to the ground state by emitting a photon, the resulting which-way path information destroys the quantum interference, resulting in the classical probabilities of half of the atoms being detected by each dx and dy. Once again, with the which-way path Mach-Zehnder interferometer, S is the source of the atoms. BS1 is a beam splitter that separates the paths A and B. MA and MB are mirrors along paths A and B. BS2 is a beam splitter that recombines paths A and B. And DX and DY are detectors. DA and DY are non-destructive detectors that detect which-way path information by causing an excited atom to drop to a ground state. Finally, if a channel is left open in both dA and dB that allow for the possibility of the photon being absorbed by an auxiliary atom, then the quantum interference is restored for those atoms where the photons were absorbed by an auxiliary atom. This shows that the which-way path information affects the behavior of more than just subatomic particles like photons and electrons, but for atoms as well. This further shows what we know or potentially know about these particles affects their behavior. In this quantum erasure, mark Zehnder interferometer, S is the source of the atoms, BS1 is the beam splitter that separates paths A and B, MA and MB are mirrors along paths A and B, and BS2 is a beam splitter that recombines paths A and B, with dx and dy being the detectors for the atoms. dA and dB are non-destructive detectors that detect the width-way path information by causing an excited atom to drop to the ground state. C is an open channel that produces a probability of the emitted photon being absorbed by an auxiliary atom. And epsilon is the auxiliary atom that absorbs the photon. This delayed choice experiment used a March-Zehnder interferometer where the beam splitters were substituted by optical Bragg pulses, BSP1 and BSP2, and the mirrors were substituted by optical pulses MPA and MPB, sending a single atom through the interferometer. In this delayed choice March-Zehnder interferometer, S is the source of the atoms, BSP1 is an optical Bragg pulse beam splitter that separates path A and B. MPA and MPB are optical pulse reflectors along paths A and B. BSP2 is an optical Bragg pulse beam splitter that recombines paths A and B. And dx and dy are detectors. After the mirror pulse was triggered, a quantum random number generator was used to determine if the last beam splitting pulse, BSP2, was triggered or not. The result is that atoms cannot tell how it is going to be detected when it leaves the first beam splitting pulse, BSP1. When the atom leaves BSP1, there is no indication as to whether or not BSP2 will be triggered. In fact, it is not determined to the last leg of the interferometer. Despite this fact, the atom behaves like a wave when BSP2 was triggered and like particles when it is not. What this shows is that the behavior of atoms, as well as subatomic particles, is only determined when they are observed. Furthermore, the behavior is based on the information available about the atoms or particles. Here is a quantum eraser with a causally disconnected choice. In this case, the quantum random generator and the idler photon detection are all separated from the interferometer by some distance. It is set up so that there is no possible way for a classical signal to go between the locations before the signal photon is detected. In the most extreme example of this, the distance between the interferometer and the idler detector and quantum random number generator was about 144 kilometers. That's about 89.5 miles. Here is an illustration of the data. As you can see, C and D indicate that when the path is not known, you get an interference pattern, but you do not get one when the path is known. Quantum mechanics is so weird, but by itself, the math does not give a real clue to what is going on behind the scenes. As a result, there have been numerous interpretations of quantum mechanics. In fact, more than I can give a decent treatment to. The following list includes the most popular interpretations of quantum mechanics, ending with a reference to the information universe. The Copenhagen interpretation was proposed by Niels Bohr in 1920. According to this view, a quantum particle doesn't exist in any one state, but exists in all its possible states at once. When a quantum particle is observed, it is essentially forced into one of the possible states, and that is the state that is actually observed. Ultimately, the only thing that really matters are the experimental results. It does not really seek to explain what is happening behind those results. It can be summed up in the attitude of shut up and calculate. Currently, it is the most popular interpretation, but it is losing ground. The many worlds interpretation was proposed by Hugh Everett III in 1957. It sees the world as constantly splitting off into multiple universes in which every possible quantum event occurs. This fits perfectly with evolution because even the most improbable events occur in some of these universes. There is no evidence for this interpretation since the alternative worlds would be forever out of reach. While quantum interference between adjacent worlds has been suggested, the possible evidence for its successful interpretation of single particle interference is not unique to the many worlds interpretation. So acceptance of this interpretation is purely philosophical and not scientific, since it cannot be tested. The fact that this allows for every possibility to actually happen in some reality gives atheists a way around the probabilities against their theoretical history. It is also an effort to save both determinism and materialism from the natural consequences of quantum mechanics. This interpretation can make it hard to accept quantum mechanics when all you have is many worlds and Copenhagen has interpretations. Pilot waves depict the quantum wave as guiding the particle. It is totally deterministic and good at explaining quantum phenomenon, but requires a large number of hidden variables that cannot be directly measured. The hidden variables also have the side effect of rendering this interpretation untestable, at least directly. One other problem with this interpretation is that it does not explain the medium that pilot waves are supposed to operate in. Furthermore, two sets of experiments show both local and non-local hidden variable theories to be wrong. Bell's theorem experiments, which demonstrate the incompatibility of quantum mechanics with local hidden variable theories, Leggett's theorem experiments, which demonstrate the incompatibility of quantum mechanics with non-local hidden variable theories. This interpretation is at its heart another attempt to salvage both materialism and determinism. The decoherence interpretation states that quantum behavior is lost through interactions with the environment. This interpretation does an excellent job of explaining the difference between the quantum effects of the microscopic world and the classical physics of the macroscopic world. It also does a good job of explaining why one gets individual particles in experiments, because decoherence occurs when the particle interacts with the particles in a screen or a detector. One of the main objectives of decoherence theory is to eliminate any need for a conscious observer in the process. The idea that a conscious observer plays any role in physics is abhorrent to a naturalistic, materialistic, atheistic worldview. In such a worldview, a conscious observer cannot play a role in physics because consciousness is supposed to be merely a function of the brain. One problem all of these interpretations have in common is that they do a poor job of interpreting which-way path experiments, including quantum erasers. The problem is that the key thing that comes out of these experiments is that the wave function collapse is based on the availability of information about the particle. What causes the biggest problem for these interpretations is the fact that the which-way path information can be erased after the particle is detected, and it still affects the results. The other problem is that they all require the universe to act differently based on the availability of very specific information, and none of these provide any reason why that should be the case. With the conscious observer interpretation, consciousness causes the collapse of the quantum waves. It is usually associated with observation. There is some supporting evidence for this, though the evidence is not exclusive to this interpretation. This view fits well with both New Age Hinduism and Christian worldviews. With New Age Hinduism, it provides a way for the mind to interact with the world beyond the five senses. The Christian worldview sees God as the ultimate mind, and it provides a model for his interaction with our world. While this interpretation does an excellent job of explaining which-way path experiments, it still has one problem. Experiments have been done when no conscious observer knows the which-way path information, and it is rendered unavailable to them, but it still exists. This suggests that rather than the conscious observer causing the collapse, that the conscious observer may determine when the which-way path information becomes permanent. The information universe falls in the general category of digital physics. However, it extends the idea, and it's a more complete theory. This theory has its roots in my personal effort to make sense of quantum mechanics and general relativity and find a theoretical background from which I could accept both. While the core concept of the universe being fundamentally information is not unique to my work, I, however, did come to this conclusion independently. It is unique among interpretations of quantum mechanics in at least 4 ways. Number 1, it can actually serve as an underlying theory to explain any of the other interpretations. At first, this may seem to make it untestable. Actually, it doesn't, because its testability is independent of all of them. Number 2, it does more than provide a new interpretation of quantum mechanics because it unifies quantum mechanics and general relativity. Number 3, it makes testable predictions about the outcome of future experiments involving which-way path experiments. Number 4, it suggests other areas of study rather than being a philosophical dead end. Each of these will be explained in greater depth in future videos of the series. The problem with most interpretations of quantum mechanics is that they lead nowhere. The information universe, on the other hand, goes beyond just interpreting quantum mechanics, but actually explains what is going on behind the math. As this theory is further explored and developed, it will likely produce new twists and turns that are not yet evident. This is likely to become more testable rather than falling into the same trap as string theory. Upcoming subjects include how quantum mechanics destroys materialism, digital physics, Planck units, key concepts, unifying quantum mechanics and general relativity, and quantum gravity. If you liked this video, please press the subscribe button to subscribe to this channel, and also give it a thumbs up. You can also support this channel with a donation by using the link in the description.